Okay, I think it's time to start. We'll wave to the online participants. Hello, my name is Mikael Johansson. I'm manager for quantum technologies here at CSC, and with me today I have Jarmo.
Hi, Jarmo Oikela. I'm the title is senior applications scientist, but like a jack of all trades, so I do a bit of everything here.
And before we go further, it would be great if someone from the online audience would give an okay that you actually hear us and see a shared screen.
Yes, we can.
They said yes.
They said yes. Okay. Let's see. The right speaker now. Can you say something? That's if it comes out of the speakers. We didn't hear it here.
Okay.
Yes, very good.
You can start and I can go.
Okay. So without further ado, welcome everyone on site and online to this Birds of a Feather / seminar on the topic of climate digital twins and their possible relation to quantum computing. That's the topic of today. Oh, didn't change the slide. A few practicalities first. Oh. There was also already, it's not changing anything. Let's restart this one. There was posted already in the chat on Zoom the link to our question and answers Q&A system, where you can ask questions constantly during the seminar, and we'll see what we can answer live here, but also everyone should feel free to reply also to questions and keep the discussion active there as well, because we have limited time and we will not be able to maybe go through everything here, but just now when we have lots of people interested in the same topic here, so it's I think it's nice to have an active discussion there. Yes, okay. And also I want to start by saying that what we will hear today should be seen just as an opening of a discussion of the convergence of these two fields of science, and not some sort of a final status that this is how things are going to be and this is how they are now. We really should keep everyone an open mind, and I think that will be the leading theme of today, that to make this succeed, we really need to collaborate across disciplines and really bring in new thoughts for accelerating climate digital twins with quantum, and or in general make the two work well together. So here is now shared the address for the Q&A. So it's siili.rahtiap.fi/climateq, and then you can also add the question mark both there to just get the editing window and the other window visible at the same time. So it should look something like this, and then you also have these buttons here where you can switch between just watching the questions and then asking. And very quickly how this works. So it's this simple markdown format. So there's samples here. So how to do it? So I just type something here, and then it immediately comes up also here live on the chat. So keep posting and asking there whatever pops into your mind, and it will also be kept as a record. And if there's something that we cannot answer directly during this seminar, then we might also add answers to this document here after the seminar, and then keep it up at least for a while after this. Okay. My mouse cursor is not cooperating at all. Okay. So we'll have divided this now into 3 parts. So we'll start with an introduction to what is quantum computing, and then we'll have an introduction to what is climate digital twins, and then we'll finish off by discussing a bit that what could we do by combining these two, maybe rather different topics, but still related to, of course, computational modeling of our surroundings. So very briefly, let's get into it. What is a quantum computer? How many of the audience here online or on-site have heard about quantum computers? Well, you have heard because you registered. How many of you have used a quantum computer? That's significantly fewer, but at least some. But anyway, a quantum computer is a device that directly exploits quantum mechanical phenomena to perform some sort of a calculation. And these quantum mechanical phenomena are superposition, entanglement, and wave function phase. So some devices also use tunneling, but anyway, the idea is that there's some quantum mechanical phenomena that you actually want to exploit to do something useful. And this is in opposition to quantum mechanical effects in normal computers where in your CPUs and chips you still see or already see quantum mechanical effects like tunneling and all sorts, but that's just a nuisance and makes the computers works less well and produce errors, and one wants to get rid of them as well as possible. But in quantum computers, you want to somehow exploit this. But at the same time, also we need to know what a quantum computer is not. So a quantum computer is not a super fast version of a classical computer. It is just completely different. And what this means is that it can speed up some types of calculations and some types of calculations even significantly, but for other types of calculations, it's no good and will actually just perform much worse than even a laptop. And this is really maybe the take-home slide already of the whole seminar here, that the idea is now to, for all fields of science, not only climate DTs, but everything, to figure out what would a quantum computer be useful for. So we should not see it as, okay, we'll just wait and then it will do everything 1,000 times faster. That will not happen. We have to figure out what parts of our calculations could be speed up by quantum computers and what types of problems could we solve with quantum computers. So we cannot just recompile now our old codes and hope that now with future quantum computers, they will just be super fast. That's not going to happen. So what we want to do is to connect quantum computers with supercomputers in this so-called high-performance computing plus quantum computing paradigm. So quantum computers perform calculations and computations in a completely different manner, and we'll see very briefly how they do that here today. And this means that, as said, so for some calculations, they can potentially speed up the calculation significantly. But actually, for most type of calculation, quantum computing provides really no advantage whatsoever. But the hope is then that quantum computing could provide an advantage in some of the most difficult and time-consuming parts of a calculation. But whether this happens or not really depends on can we get the software in place. But this means anyway that what we will have in the future is this hybrid supercomputing, classical supercomputing plus quantum computing infrastructure that we will perform our calculations on. So quantum computers and supercomputers will merge, and both actually need each other. We know that there are things that supercomputers will not be able to ever calculate because it's just too difficult. But at the same time, also quantum computers cannot calculate everything. And just to operate, they will need classical computing power, significant classical computing power for a long time. And actually, the more powerful the quantum computer is, then usually the more supercomputing power it needs sitting next to it just to take care of compilation and all sorts of other things that we will not go into detail in today. But then, just to drive home the point of how these two computer types are different, let's think a bit of how the standard classical computer is controlled. So in our laptops and all other classical computers, binary computers, the information is stored as bits. This we all know, so they are either 1 or 0, and the memory is full of these ones and zeros. So we have these bit strings 1 1 1 0 0 0 1 1 0, so forth. And when a computer does something, so really at the basic level, all that happens is that ones becomes zeros and zeros becomes ones, or they don't change at all. So if we go really to the basic level and think of what a computer program does, so it's simply a recipe for which bits to flip and when to do it. So it's a rather simple system that everything complex is then built out of. A quantum computer then, as mentioned in the beginning, exploits these laws of quantum mechanics. So it doesn't use bits, it uses quantum bits, qubits. And these qubits can then be, you have heard this, 1 and 0 and everything in between at the same time. So it can be either in the state 0 or in the 1, or then in some sort of a combination of 0 and 1 with coefficients alpha and beta here. This means that the quantum bits are much more versatile than standard bits. And now this alpha and beta that we have here in the combination of 0 and 1 are complex numbers, so they have a real and imaginary part. In practice, this means that they can be represented as points on a sphere. So every state combination of 0 and 1 can be represented as being somewhere on this Bloch sphere, as it is called here. Let's see if I can get the cursor there again somehow. He's escaping me. I don't know if you can online see it at all, but anyway, this is supposed to be a sphere, a ball, a three-dimensional creature. And I am marked here by blue the North Pole and red the South Pole, representing the states 0 and 1. And in a classical computer, these are the only two states that are accessible. So you can have your bit either as 0 or 1. But the qubit can be then any point here on a sphere. For example, this orange dot up here. Or I've also marked here with this green circle the equator, so to say, where we have an equal superposition of 0 and 1. But also here we can immediately see that the equal superposition is not just one point on the sphere, so it is really much more complex because depending on the wave function phase, you are somewhere on this circle. So from this one already sees that the information content in a qubit is, well, in principle infinite, because depending, of course, on the precision, how you define it, in practice it will not be. But anyway, it's much more versatile than just a bit. So you can cram much more information just here. And at the same time, this means that the operations that we do become much more complex, because now we can do much more than just flip from 0 to 1 and 1 to 0. And we also have to do this, because otherwise the quantum computer is just a crappily working classical computer. So you really need to take advantage of the fact that you can put your basic information unit, the qubit, into any state on this sphere. So one can also compare the Bloch sphere to the Earth, just for visualization purposes. And I already mentioned that we can have North Pole here as 0 and South Pole as 1. And then just made a video here of what it actually means when we do some manipulations on this sphere. So North Pole is 0, and if we now have a classical computer, all we can do is flip the bit so it goes to the South Pole. So we jump to the other side. But in a quantum computer, we really need to go everywhere on the surface of this sphere. So we can go to the equator where we have a 50-50 superposition of 0 and 1. But we can also go somewhere else. We can go, as many of you already did today, come and visit us here at CSC. And we really need to jump around on the sphere. That's the point of this video. And then we can go again on the other side of the Earth to Australia. But we don't only do these big jumps here and there. We also need to do these very small adjustments by moving just a bit on the sphere. And this is where it becomes technically very tricky. You want to do this, but really to get this precise control is, from a technical point of view, very difficult. And this also, maybe I can say it already now, is that when trying to program quantum computers, you actually have to take into account the physical reality that quantum computers are not perfect. When you program for a classical computer, you trust that everything works perfectly and you don't need to worry about precision and such. It's defined by different standards and you have double precision, quadruple precision, whatever you need. But in a quantum computer, this is much more fluffy. And you cannot just wait and hope that the fluffiness goes away. You will have to live with imprecise quantum computers for a very long time. So when we then combine this superposition with quantum entanglement and this manipulation of the wave function phase, we really come to a quantum revolution and we can do some things extremely efficiently, at least in principle. But before getting any results out of the quantum computer, just like a classical computer, we have to program it. So we need quantum algorithms. And this is really very different from programming classical computers. And you already got a hint of that by seeing this, that we really need to already just manipulate the qubit state so that it really moves around the sphere. And this is just for one qubit. It gets much more complex, of course, when we have more than one qubit. So just to see a bit how the parallelism works when we have this superposition. If we think now of a classical computer, we have 2 bits, then we can have that in 4 different states, 0, 0, 0, 1, 1, 0, and 1, 1. And if we want to compute some function for this, we need to do it 4 times, each with 1 input here, and then we get the value for these 4 different inputs. But in a quantum computer, what we do is that we create this superposition of all of these input states. And the blue bump there is supposed to now show the weight or the wave function of the state with the idea that it is now an equal superposition of these. And now we can feed in all of these 4 states at the same time into the quantum computer and have it calculate some, well, this is now a fancy function because this is a quantum computer, so the F is fancier, but it just computes the value for all of these at the same time. But it doesn't only compute the value, it also has to manipulate now the amplitudes here, or the probabilities, the coefficients alpha, beta, gamma, and delta here, in a way that somehow enhances the correct answer, however you want to define that. Because even if a quantum computer can take all of these 4 inputs and handle them at once, it will also, one calculation always gives just one answer. And then the idea is that at the same time as you do the calculation, you also need to take care of somehow enhancing the probability of the correct answer coming out of there. And here the correct answer would then be the, well, whatever function of the 0, 1. But we also see here that these other bumps, you can, in practice, you can never get them completely to disappear, which means that there is some probability that you will get the wrong answer out of an algorithm. This is now, of course, very simplifying wording, but a quantum computer is supposed to give different answers for the same input. So it's a probabilistic calculator, which is also something that you really need to take into account. So there's lots of new things to think about already just conceptually for trying to figure out how to use this. I put this example here, the traveling salesman problem, as an example of a problem where you have many potential solutions, but only one that is interesting. And this relates to the previous slide where we really would have many potential solutions here. Let's say that this FX now computes a traveling salesman problem. And then all of these different possible answers would be the answer of all different possible routes that you can have. But quantum computers give only one answer, and then you want to also solve problems where only one answer is interesting. And for this, the traveling salesperson is a very good example. So the problem is to find an optimal route that connects a set of n points. So here, for example, we have 5 points, and then you can connect them in different ways. And this is a problem that is always surprisingly complex to solve with a brute force fashion. So there is actually n-1 factorial different options to connect these points. So already if you have 4 cities, 4 points, then you have 3 factorial different routes, which means that you have 1 times 2 times 3 equals 6 options. If you have 5 cities, then you multiply that by 4 and have 24 options. And this really immediately blows up the problem. With 10 cities, so this you can still do on pen and paper, and it is actually instructive to do so and really see that, okay, yeah, there is actually a shitload of different options. With 10 cities, you have over 300,000 ways of connecting them. And it, at first sight and even second and fifth sight, it seems like, no, it cannot be, but it really is. With 20 cities, you have, I had to write it down because I always forget how much it is. It's 121 quadrillion different options of just connecting 20 points. But of all of these points or different options of connecting them, we only want one answer. We want the shortest route or the best route by whatever criteria. So this is an example of a problem where you have a rather limited set of input data, the coordinates of some cities or whatever points, extremely large potential solution space, but only one answer that you're actually interested in. And these types of problems are really good for quantum computers. Okay, we always have to remember that classical algorithms don't do this in the brute force way either. We have to compare to the best classical algorithm when we want to do something. The traveling salesperson problem has really been studied extensively, and the record now, I think, is that there's more than 1 billion stars from the Gaia map or data set that have been connected with an error of less than 1%. So one knows that it's maximally 1% too long. That can be mathematically somehow proven. So the traveling salesperson problem as such is not really something that you want to spend too much time probably trying to solve on a quantum computer. There's already super efficient classical solutions to this that are approximate, but they are anyway more than good enough. So this is an example of a type of problem that quantum computers potentially can be good at, but at the same time it's an example of a problem that, well, for academic reasons, you might want to find a very good quantum algorithm for the traveling salesperson problem, but the practical utility of that will not be very important, at least not directly for this. Of course, then you can refine it and do some other sort of constraints on the optimization problem, and then it might become interesting, but we need to keep this in mind all the time. So there are, however, several other optimization problems that, unlike the traveling salesperson problem, are very difficult for classical computers. And here the electronic structure of molecules and materials is one of them. And where you want to, in practice, optimize how the electrons are situated and located. The electron cloud looks like around specific molecules, and from that then derive all sorts of properties of how drunk you get from ethanol. But also here, we have to keep in mind that classical computers are already very good at this, and for some, but then there are chemical systems, for example, that are very tricky also for even for supercomputers. Okay, and then one slide here on the noise problem. Qubits are very delicate, so their states, the state there, wherever it is on the surface of the blogosphere, change due to outside influence in a way that you don't want them to do. So this is called the noise. For example, temperature or electromagnetic radiation or whatever. And this can lead to, for example, that the superposition is lost, and which crashes the computer. Or it can also just change, for example, the phase of the qubit, or just move it out of the position that it's supposed to be in. And this also affects the way algorithms have to be created, because they have to be resistant to these small changes. In a classical computer, it's easy when you have just 0 and 1, because then you know if it goes to 0.1, then it's still 0. Let's say we have a voltage that defines 0 and 1. So we have 0 volts or 5 volts. That's common in this older computer. So if you have 0.2 volts current in your transistor, then that's at 0. If you have 4.7, then it's a 1. But in a quantum computer, you really want to have this very fine control of where it is. And then being 0.1, it's supposed to be 0.1 probability of or composition of zero of the state 0, for example. So there you cannot use this easy error correction that if it's almost 0, then it's exactly 0. It becomes tricky, both from a technical perspective, but especially also from an algorithm perspective, because you have to, for a long time, consider this. Okay, a quick slide on different quantum computers. There's quantum annealer simulators and an increasing order of generality, and continuous variable quantum computers, and then gate-based quantum computers. And I'll just quickly show the basic principle of how to program a gate-based quantum computer to get an idea of how you get out the quantum there. So when you do some quantum operations, also called gates, on the qubits, you do some rather simple linear algebra. So the qubits themselves are vectors. So the 0 state is the vector 1, 0, and the 1 state is the vector 0, 1. And then the operators for this are matrices. So for example, the not operator that flips the state of the qubit and bit looks like this matrix. And then when you apply this quantum operation on whatever state, you just perform the linear algebra where you take row times column and see what you get. You have 0 times 1 is 0, and 1 times 0 is 0, and so forth for the next row. And you can do this exercise by yourself at home, but then you see that, well, the state 1, 0 became the state 0, 1, so 0 became 1. And these different operators, there's lots of them, you then combine together to write your algorithm, and this is often represented as these circuit diagrams, where, for example, the circuit diagram for not on the state 0 would look like we start from the state 0, then we go, so the time goes here from left to right, then we do something here, the X operator, and what we get out is 1. So that's like a very simple representation of circuit diagram. And then I just want to show still this one, because this is really central to quantum computing. So it's the Hadamard gate, which puts a state into a superposition of both states, of two states. So as an example here, we have the Hadamard operator on 0, and the matrix for this looks like this one. We can ignore now the normalization factor there. But now, without going through now the mathematics here, you can do it quickly yourself. We see that if we do this operation on the state 0, what we get in the end is a combination of state 0 and 1. And this is now the superposition state, and it's an operator that you, of course, cannot do on a classical computer. And this is really the basics that you almost always start your quantum computations from. You want to, in some form, you want to create this superposition of states. Okay, and then you combine all of these operations into algorithms. And for the moment, if you want to really create something new, you really need to program at a very low level. So here's just an example of some start of an algorithm where you just denote all these different things that you do to the qubits with these boxes, and then you go from left to right and just perform these operations on the qubits. But already, of course, there is in the making all sorts of libraries that would do the basic operations themselves, and then you just need to figure out that which kind of operation would be useful for this problem and so forth. So it is getting simpler as we speak, but still it's good to know the basics of where this comes from. So the summary so far is that, well, we already have quantum computers that can outperform the best supercomputers, but it's not really for anything useful yet. We need to develop algorithms that are short enough so that they actually complete before the quantum computer crashes. And the algorithms also need to be able to, at least in principle, compete with classical algorithms and supercomputers. And this really is a multidisciplinary problem. So we need to combine knowledge from all sorts of fields, and especially also from the application field. And that's why we are here today, that we really need to have this. One needs a deep understanding of what is the best that one can do right now for a specific problem. But then one also needs to know, in computational science, we always have all sorts of approximations and a feel for why does this work and why doesn't it work. And one needs to have this domain-specific knowledge to really know what is now the big problem or the small problem with his model. So it's not always just a mathematical problem. You cannot look at it like that, because then you just analyze what is being done now. But you have to also think of what are we not doing and why are we not doing it, and what would we want to do if we could do. And we really need both software and hardware in place so that we can get this quantum revolution going. And with this, where I went badly over time, I'll switch. We will switch to Jarmo, who will tell us about climate modeling.
Okay, first I'll start with something else. So what gave rise to this BOF is that we were part of this larger team that was writing a report to ESA about where can we use quantum computing and quantum algorithms and how to use it. And one of the kind of use cases there, it's taking a bit time to switch the size, was this climate change adaptation digital twin, which is one of the digital twins here at we are developing at CSC, or CSC is leading their development. So this is part of the Destination Earth program, and this wasn't really, it was supposed to be a kind of just a setup slide for this. So what I'm going to talk about is a brief recap on what are Destination Earth and what's the climate adaptation digital twin. Then we are going to continue a bit about this climate simulation workflow and what's the key differences to traditional climate modeling. So this workflow is directly related to the digital twin. So then we'll take a bit of a look at the poster now. Okay, yeah, it's giving me stuff that I don't want to see, but it's nothing to worry about. So then what's calculated inside an Earth system model and which parts are resource heavy. So this was done to kind of see if something could be accelerated with quantum. And lastly, is it possible to achieve any acceleration? And then I'll think we'll continue with Mikael after I can wrap it up, and then we'll discuss something afterwards. So there's Lumi picture also. So you have to have a picture of Lumi CSC presentation. Someone is requesting to record this, and I can't see my slides there, but I'll see them there. Okay, so what's the Destination Earth program? So it's a European Commission program for developing digital twins, and the target is to get a full replica of the Earth by 2030. So the climate adaptation digital twin is one of the first being developed. There's also the Extremes digital twin, and there are also kind of complementing efforts like the biodiversity digital twin. So these are implemented by ESA, ECMWF, and EUMETSAT, like procurements, and the climate change adaptation DT is led by CSC, so we are doing this work for them. And the climate DT, the purpose is to assess the impacts of climate change. So this means that we are just not simulating something, we are trying to see what kind of impacts and which adaptation methods, for example, or mitigation strategies have some kind of impact, and what kind of impact they have on the climate, both on local and regional levels, but it's global simulations. And the phase one, so it's a 5 kilometer global mesh. So this means that we have a grid point every 5 kilometers. Like that. And in the core of this DT are two climate models, the IFS FESOM. So this is from the ECWMF, so the European Center for Medium Range Weather Forecasts. and the ICON, which is from basically led by MPIM, so the Max Planck Institute for Meteorology. They also have the German Meteorological Institute, and things like these involved. Those are the kind of members. So that's the Destination Earth program, and basically the climate DT. Very briefly, it's a large consortium, 13 members, and this is why I really like PowerPoints, because I did this in LibreOffice and nicely done. Doesn't matter. It just says the information on the background just mentions that there are 13 kind of consortiums that have expertise in HPC and climate modeling and things like this. I'm not going to read them. I think most of you have heard of this, so maybe we'll give out the slides at some point. But so from Finland, FMI, and University of Helsinki. Okay. So this is now the rethought climate, so the workflow for the climate DT. So we have two models. So the IFS FESOM Nemo and the ICON. And what is a traditional way of doing climate simulations is that basically I'm referring to CMIP protocols, so coupled model into comparison projects. So CMIP 3, 5, 6, whatever you want to choose. So basically you have this, first you form a consortium that discusses and develops these kind of scenarios that you're supposed to run. And then you mash it out a bit, like a year, 2 years, 3 years. Then you come up with these protocols, and then you run the models themselves with these protocols. And I put there approximately 1 degree resolution. So for CMIP 5, that's 1 degree, and for CMIP 6, you get a bit, depending on the MIP. So there are multiple types of simulations done, but that's usually the resolution. Then you upscale it or downscale it to a much denser resolution. But the process itself is slow. It takes multiple years. It takes a lot of effort, and there's no kind of interactivity with the end user. So if you want to kind of have some kind of impact on what's the actual effect of some mitigation strategy or some kind of other kind of thing that you want to do with so example, putting something in the soil to increase carbon sink or something like this. So there are some kind of some specific MIPs for that, but very, very good. So that's kind of one of the reasons why this was developed. So here the idea is that we are integrating applications into the workflow itself. So we have 2 climate models that take a crap load of input data, and then they output some kind of output state vector. And then we generate this generic state vector from that. But when we are increasing the resolution from this 100 kilometers to 5 kilometers or 10 kilometers, we are also increasing a crap ton of the data itself. We are also increasing a lot of the CPU resources or GPU resources needed for this. And basically CPUs wouldn't type anymore. So the idea is to combine GPUs with the models. We are also streaming the data from the models directly to the applications. So this means that we are taking the data or what the models are outputting directly from the memory and forwarding them to applications. So that data is not going to be saved on the disk, or let me rephrase it. Snapshots of the data will be saved to the disk, but not that much. So if you think about a typical climate simulation with a 5 or 10 degree resolution, it could easily get about a petabyte per day. So, and actually, I think the throughput for these models that is kind of hoped for is 1 simulated year per day, and that would be about a petabyte per day, I think, of the data. I'm trying to remember it, but it's not there. And the final thing thing is that when we are going to stream it, the data that is going to be available for the applications is a rolling window. So we don't discard data immediately, so it's saved about a month or so worth. So this data will be rolling forward, and when it's available, the applications just take it the new data. And the other parts of this workflow, the quality assessment and uncertainty quantification is an important part, as well as the data bridge and the data lake. But for the purposes of the quantum computing part, I'm not going to go in. So what am I forgetting? Yeah, the last one. When we increase the resolution, there's a kind of option that we could also include some kind of new kind of processes, new kind of physics into the model. And also, what's the benefit of this is that we can get a direct comparison with observations or make it a bit easier. So, for example, with the in-situ towers and stuff like this. So you don't have to upscale and downscale and do all kinds of tricks. But still, especially when we increase the resolution, the models are going to be the bottlenecks in this workflow. So they are the ones that are going to define the speed of how this flows. I think I'm going to take extra time as well. So almost the same slide as the previous one, but this one is more about what are the benefits of the streaming. So full access to the model state. So basically the generic state vector when it comes available. So this is the rolling 30-day window. And interactivity. Interactivity, scalability, and handling of huge amounts of data. Basically for this, I would say also that always in the scalability. Yeah, when you get to new applications or add something to this, when you get some ideas, it's easier to add applications in there. So this is basically supposed to be running full time, all time, and then you get data and you can use it. And this is just a reminder for myself that what are the first use cases. So there's wind energy, extreme events, freshwater availability, wildfire risks, and stuff like this. This is just to let you know that what's been planned. So it's nice to know it's not that important for the one. And now a typical Earth system model. So all kinds of things going on there. Basically, there are three parts. There's atmosphere, then there's some kind of soil thing or land, and then we have oceans and rivers and stuff like this. We also get all kinds of ice sheets, glaciers, and things like this, but they are not. They are additions to the models themselves, and some models have different kind of aspects in there. For example, the human contributions and land cover changes and things like this. But basically, you have some kind of atmosphere thing, some kind of ocean, and some kind of land surface. And what this means is that these kind of different kind of parts of the model have different time steps. So it's not very beneficial to take something like, say, how much terrestrial carbon is I don't remember the word. Degrading? No. Turnover rates of the terrestrial carbon, how much is affecting like something like wind speeds or something like this. So basically what we have is the atmosphere, which has the lowest time step. And that defines a lot of where the computer resources are going into the models. So also when you have like ocean and land, all of them are important there, but the atmosphere usually defines like we are interested in how warm it's going to be and where are the winds going and torrential rains and things like this. So yeah, sorry, this is from the ICON model. So the ICON A is the atmosphere, then ICON L is the land model, which is called JSPOH. It's down there. And the YAC is the yet another coupler. So it's just a coupler between all of these. And the ICON O is surprisingly the ocean model. So this is just to show you that the time steps are really different. And we all couple these models together, or we let them interact with each other only at certain times. So pushing forward the atmosphere doesn't mean that we are also pushing at the same time all the effects to the ocean or all the effects to the land. That's kind of the purpose of this slide. Different time steps. And also when you think about it, when you have like the atmospheric model, and you have all these layers, and then you have a 5-kilometer mesh, you end up with, let's say, a crap ton of points. And then at each time step, you are calculating the same things at each grid point and pushing it forward, and then putting it forward again and putting it forward again. Because it's chaotic, you really have to have small time steps to put it in. So this is about when we went into the actual kind of code, so analyzing calculation costs, so how much resources does it cost to drive the atmosphere model forward, and what parts of the model are taking most of the resources. So previous work, for example, on the CP-MIP is used as well. So we don't only do some kind of simulations and try to get the information from there. So we also use literary resources for this. But this is a snapshot of single IFS simulation. So you can just, it's very indicative of where the resources are going. And this is, as you can see, there's 0.12 on average the resource use and 0.18. So this is just a small part of the actual report from there. So when you change the way that you are running the models forward. So when you change the resolutions of the ocean atmosphere, because you can change them differently, then you get different results and different parts are taking more time or less time. That's to kind of keep things going. And we put some categories there, or I did. I'm trying to decipher the meaning of the PuTTY name. And so that was all about, yeah. So this is almost the last slide. So the major components of a typical ESM, so we kind of discussed this. So we have atmosphere, which is roughly taking about 90% of the resources, and ocean, which is taking 10, and land surface, which is taking a small amount. That's it. Like this is different for different models, but just to give you some kind of approximation of where it's going. Then what's calculated in each part? So there's temperatures, winds, radiative transfers, clouds, things like this in the atmosphere, and also heat and carbon dioxide uptakes in the ocean. So also there's heat transfer in the atmosphere. And the basic idea is that you actually do get some similarities in different parts, both in atmosphere and ocean. So based on these, what kind of calculation do you think that is being done there? So the guiding equation, this is an example for the atmosphere. So there's a lot of differential equations. Then Navier-Stokes is probably the most important here. So they describe the fluid flow. So basically how momentum, heat, and stuff like this works in the atmosphere, how it's transferred from grid point to grid point and so forth. These are partial differential equations, basically. Then we get the heat transfer, which is also surprisingly differential equations, and then cloud model physics as well. Additionally, we do have some algebraic equations like the ideal gas law and things like this. There's vapor pressure is also kind of calculated similarly. I've added the parameterizations there because, as we mentioned before, if the grid resolution is very large, then we have to kind of somehow simulate the processes that are sub-grid scale. And that means that, for example, the cloud formations, this has meaningful, the parameterizations are meaningful. And when we go to the smaller grid sizes, we can try to get some kind of other processes in there. So we don't just have to parameterize everything, hope for the best that it works. Also, when you parameterize something, it should work globally, or then you have to parameterize everywhere. It's really frustrating. So the simplified representation of convective flows is also an example. And what does this have to do with quantum? Thanks for keeping up with me. So this is the last slide I'll be talking about. So almost all of these I said already. So just to recap, it's the climate DT is a new type of climate information system. So we are trying to simultaneously run the model and forward the data to the applications and get some kind of impact or feedback from the adaptation techniques and assessments. There are a plethora of calculations inside the models. So, for example, the fluid dynamics, which is one of the potentially benefiting from quantum leveraging. But I know that you guys are going to say something about this, so I hope. And lastly, the higher resolution makes it possible to get some kind of smaller scale physics and processes. Thanks. I'm done. Finally.
Yes, high five. Good. Yeah, there is indeed something on top here. Yes, so now to the final part. So how can we combine these? Well, let's have a new look at this the time-stepping figure that Jarmo just showed as well by Honegger. If we just look at what this means, so we can see that there is this roughly 1 to 30 ratio between the shortest and longest time steps. So there is a difference, but well, it's 1 order of magnitude, so it's not like a huge difference. So the whole time for computing these individual time steps range from the sub-second regime to around 10 seconds on an example run that we now did on the latest version on the LUMI supercomputer. So computing the time steps doesn't take very much time. We'll come soon back to that. Then we can also see that some other observations on how the climate models are being implemented now is that, well, the amount of data is huge, as mentioned. So already, if you have a grid resolution of 10 kilometers, then we have hundreds of millions of grid points representing the atmosphere. And each of these grid points have several variables, about 20 or 30, depending on the model, I think, associated with the properties of that grid point, like air density, temperature, wind speed, humidity, and so forward. So it was this, what was it, petabytes of data, terabytes per data per day. Here I even get the scales wrong, but 1 petabyte, I think. Yeah, so the amount of data for just representing a static picture of the atmosphere is really huge.
Also, the 1 petabyte was what's coming out of the model. So
okay.
Yeah.
Yes. But anyway, yes. So we have lots of data. So already from these 2 observations, we can really identify 2 main challenges that make it difficult for quantum computers. It is a big data problem, and we have a rather short wall time for the individual calculations when we propagate the model in time. So the big data is not really directly suitable for quantum computers. A bit like we mentioned there in the introduction, so quantum computing is and quantum computers are good with problems that have a moderate amount of both input and output variables. We'll not go into the technical reasons why this is, but this is a fact that will not change for a very, very long time. So the relation now between the input and output should ideally be some sort of highly complex equation or problem that can be solved efficiently by some quantum algorithm. So quantum computers typically excel at the problems that have a large potential solution space. Think again of the traveling salesperson problem, but only a small set or even just one single solution that is of interest. And additionally, well, the amount of input parameters have to be on the same order of magnitude as the amount of qubits that we have in our systems. And we might reach 1,000 qubits by the end of the year, but that's very far away from petabytes. So this tries to somehow show what we need. We need something where you have a rather limited set of input data, but then from that input data, you have plenty of different potential solutions and a very complex way of figuring them out. And then out you should get ideally even less actual information. But this is the big data problem when you want to combine climate modeling and quantum computing. The other one relates to the time step. We really need to solve sufficiently complex problems in a very short time. So for any sort of quantum advantage, at least as measured by time to solution, you need to have the quantum computer solve something that is actually difficult. This means in practice that the algorithms have to be sufficiently deep, as it said there. So they have to be long enough. They have to do several of these basic operations gates after each other, and thousands, hundreds of thousands, millions. So the number really has to be high. So this means if, for the first, you can do this calculation, it means that any single useful quantum calculation will take on the order of at least seconds to complete. Many of those that have been proposed to take hours. So there's, for example, the famous paper about factoring RSA 2048 with 20 million qubits in 8 hours. So these single calculations for quantum computers where you actually get some real advantage, they will not be short. Okay, we should mention that variational circuits, so there the individual shots or circuits can be faster, but the whole time to solution is anyway rather long because you need to have several iterations even of these shorter hybrid algorithms. And then we remember shown that already now the shortest individual time steps in the climate digital twin takes less than a second, and even the longest about 10 seconds. And this is the situation now, and the whole aim of the Climate DT project is to speed up these time steps by up to a factor of 100. That might be an optimistic view, but that can anyway be the target. This means that all of the time steps that we are looking now will be sub-second calculations. This means at the same time that quantum computer, there's no way that they can speed this up further because anything useful takes already much longer than that single calculation classically. Okay, that might sound quite pessimistic, but let's instead then think of what we can do instead. So at the first glance, the climate models seem, as they are implemented now, seem to be rather unsuitable for quantum acceleration. But in order to get some quantum advantage, we really need to consider the problem from a broader perspective. So as mentioned already earlier, just attempting to make some sort of quantum versions of the presently used classical algorithms and the approximations that one uses there will not work. So in the medium term, advantage can only be found by really approaching this problem from a completely new angle and thinking of how to utilize the unique features of quantum computing. And maybe in the long-term, far future, when we have these fault-tolerant quantum processing units that would be integrated onto the same chip as the classical ones, then one might be able to do some useful quantum computations that also are on the millisecond scale or microsecond scale or at least sub-second scale. But that might happen, and if it happens, it's decades away. So we cannot, if we actually want to now utilize quantum computing for something, we cannot just wait and see and hope that quantum computers will become perfect. CFD, computational fluid dynamics, was mentioned, and a large part of current workflows are in effect CFD somehow. And this has a direct connection to solving linear systems of equations. And for this, there is actually well-performing quantum algorithm, the HHL algorithms and refinements thereof, which means that there is actually a potential to speed up CFD. And it has been noted also that for the moment, supercomputers are very efficient at solving matrix equations by sidestepping the need for matrix inversion that is often found in these equations. But then you just do it in some other way that uses lots of resources, but at least makes it possible to invert very large matrices. But if you now think of the problem again, so this is an approximation that you want to do. So you don't do a direct inversion, but you just approximate it somehow. And often they are good approximation, but they anyway are very resource intensive. Quantum algorithms don't need to do this because there are quantum algorithms that can efficiently, in principle at least, perform matrix inversions directly. So there's no need to circumvent this problem anymore. And then now the next step is to think that how would we put this into the model and stop doing a specific type of approximation and replace it with a quantum algorithm that just does it well from the beginning and doesn't use lots of resources for doing it improperly. This is just an example. I have a few examples here now just of how one could start approaching the problem. And the other one is enhancing machine learning. So machine learning and AI and the use of them is increasing everywhere, also in climate models, climate modeling. For example, for CFD, there's a promising approach where one can reduce the grid size without losing accuracy by just performing machine learning interpolation. It was at least discussed that for climate models where most of the effects are anyway rather smoothly changing, this could be a rather good way of speeding up calculations by at least periodically for some time doing a coarse grain grid and just interpolate by machine learning how it would look if it would have kilometer resolution or sub-kilometer or whatever. And this then connects to quantum machine learning. We don't have time to discuss that in detail today, but it means that quantum machine learning actually has some chance of doing something useful here. QML has some potential advantages, but again, we have to remember that classical machine learning is immensely powerful. But instead of speed up, we might expect quantum machine learning models to give some advantage just because they are doing things differently. So there's a potential to get by with less training data. It is being discussed actively, and I think most of these things we will not know before we have sufficiently large quantum computers to run actual real-life models, because for most problems of interest, it's not sufficient to just know the mathematical worst case or best case scenarios. Usually the real truth of practical applications has nothing to do with the mathematical limits, but it's somewhere in between. And also it has been shown already, at least for small data, that, for example, in neural networks, adding some quantum layers in there, in addition to the classical good given advantage in accuracy or speed in number of iterations in training the models. So there is potential here, but this is more of a general where quantum machine learning coupled to the machine learning of climate DT can help. But then maybe the most interesting part, well, okay, that's a value statement. An interesting part would be looking at the missing ingredients in the model, or these so-called forced approximations, where we know that we should not do it, but we have to, because otherwise it takes a million years to compute. Some physical or chemical or dynamical processes are left out just because they are too expensive to model. And then one tries to convince oneself that it's not that big of a problem. But here, quantum computing really could reduce the computational complexity, at least for some parts of these forced approximations, so that we actually can include more parameters, more physical processes in the model. And I want to finish here with mentioning atmospheric chemistry. Accurate modeling of the atmospheric chemistry, what is going on, would be highly beneficial. This is just a quote from one paper that says directly that climate models indicate at least a 30% uncertainty in aerosol direct forcing and 100% uncertainty in indirect forcing due to aerosol cloud interactions. And this is chemistry. The reason it's left out is because it's very challenging to model. Atmospheric reactions are, even if it often have rather small molecules, they are very difficult to model because we have these radicals with free electron pairs. They are so-called multi-reference systems from a quantum mechanical or quantum chemical perspective. There's photochemistry involved that is very difficult to get right. So these problems and solving these problems really scale exponentially with the size in the limit of sufficient accuracy. You can, of course, do crappy calculations, but then that doesn't really give any useful data. On the other hand, this is a perfect problem for quantum computers, because quantum computers really initially even were invented because one saw that these sort of quantum mechanical problems that also atmospheric chemistry belongs to will always be much too difficult for practical computers. But with quantum computers, there would be the possibility to include, for example, atmospheric chemistry into the models. Okay, some summary. As they are now, the digital models of climate are not very well suited for quantum acceleration. But that's just if we think of how they are implemented for the moment. So we have large amounts of input and output data, not good for quantum computers. We have short wall time of the individual steps. Quantum computing will not make them shorter. It's impossible. But still, quantum computers do have the potential to enhance climate digital twins by smart use of quantum algorithms. That's, of course, a very general statement. Enhancing machine learning, that's already more concrete. And then really introducing missing physics and chemistry. And cloud models is, for example, one where potentially quantum computing could help. But the whole idea is also that we need to somehow probably think of how to get rid of these small time steps, and that's the only way of doing climate modeling. We would need to get in a way where it's useful to do calculations that take minutes or hours even on this. And for example, for atmospheric chemistry, in practice, it would probably mean that we need to do highly accurate calculations on quantum computers and then parameterize them and put them into the model. But anyway, we would have a model to go back to and lean on to. In general, we need to start making all the computational workflows quantum ready. Even if we would have a sufficiently powerful quantum computer right now, we would get 1 million qubits, perfect qubits. There would be no software to actually utilize it. It would not speed up climate DT at all because no one would have written the software for it. And it's also crucial for HPC and quantum to work together and identify these problems that are a bottleneck. And in general, this figuring out how to quantum accelerate something is, well, it is very hard, but it is also potentially very rewarding. Okay, we have some time still for discussion here next, but I want to again go back to the first slide there that whatever we said here now should just be taken as an opening of a discussion that will not only take place today, but it's a discussion that needs to be had for a longer term, and it's not some sort of a final status or and also you should not consider now that this is the ultimate truth either. The whole idea here is that if we want to succeed with quantum acceleration, then we really need to discuss with each other and have all sorts of different viewpoints and insights that one gets from being an expert in a specific field or something. Is it mathematical algorithms? Is it quantum computing? Is it knowing what the climate DT model actually does and so forth? But I want to finish just by acknowledging, Jarmo already said this, but well, the discussion today was sparked and is also partly based on this Quantum Advantage for Earth Observation project initiated by the European Space Agency, and we are the project members here, and it was led by DLR in Germany. But we thought that it would be nice to present the results also for in this format. And with this, I thank you. And